So I recently built this interactive game. You have to guess a number and you have three, say, helps you can get. The number is between 0 and 20 and you can know either if it's pair, prime, or if it's a multiple of 3. But you can't get all the 3 helps at the same time. You only have 2 of them available and you have 3 tries. Send the command H and it will print the help message again if it's prime and the number is prime. A multiple of 3 and I'll send E and the number is not a multiple of 3. So it's prime, it's not a multiple of 3. So to send an answer I can't just send 13. It will tell me that it's an unknown command, so I have to add n and then send 17. This is your first attempt. It's not 17. Let's try 7. Let's now try 13 and I lost. So if I don't input anything for 10 seconds, it will default to no and my number was 2, terminating the game. And as the game terminates, it will just keep on printing the first 1024 digits of pi. Like the goal behind this game wasn't to actually develop such a game because it's a very simple game, as you can see. It was fun to come up with, but the impressive thing or the feature of this game is that all flags following advancement of the game were decoded into 1 byte. Before we go into how I got to do all this in a single byte, I'll have to talk to you a little bit about bitwise operations. Okay, so what you can see in front of you is the bit binary NOT operation. You see here 2, which means base 2 or binary, and NOT in C or C++, we can write it with the tilde symbol. So tilde of 1 or not 1 is 0 in binary, and not 0 is 1 in binary. Very simple stuff. So moving forward, this number is 85 base 10, so decimal. This is the 85 that we use in our life, which in hex or base 16 is 55, hex 55, and in binary 0b is 01010101. And as you can see, this is the reason I chose 55 or 55 hex or 85 is because of the alternating pattern of 01010101. Anyway, so the NOT of 85 is the NOT of 0x55, and as you can see, it's like just as we applied the NOT operation to the single bytes in the previous example. Here we just applied the NOT operation to all bits, so each one became 0 and each 0 became 1, and this is called bitwise NOT. And as you can see, the result is alternated, and we have now 170 decimal, which is AA in hex. So this is bitwise NOT. Now this is the OR operation, and 1 or 1 is 1, 1 or 0 or 0 or 1, which is this line here, it's 1, and 0 or 0 is 1. Basic. Now we have this number here, which is 240. In binary is 1111 0000, or this is this is how we apply OR in C or C++. 0b binary 00001111, 4 zeros followed by 4 ones. This gives us the binary number 8 ones or 0xFF or 255 in decimal. So how we applied this OR, we got this number here, which is 15. We brought it just for visualization manners. We brought it under here, and we just ORed each bit, 0 or 1, we said it's 1, 0 or 1, we said it's 1, same here, and 1 or 0, we said it's the same thing. So, and this is how we got all ones or 0xFF in hex. And this is the bitwise OR. and it's called bitwise just as the not because we apply it bit by bit. Anyway, and it works on numbers like longer than 8 bits. So this is the AND operator, and as you can see, 1 and 1 is 1, but 1 and 0 or 0 and 1, it goes both ways, is 0, and 0 and 0 is also 0. So same thing when we applied it to the same example of the bitwise OR, and I think you now see where we're going. We we bring this number 15 under here, we apply it bit by bit, and this is how we got all zeros. And this is the bitwise AND. So in summary, we have bitwise NOT, bitwise OR, and bitwise AND. So a little example. Here I have 255 or 0xFF in hex, and which is all ones in binary. And here we have my alternating example, which is 55 hex 55 or 0101 0101. Anyway, so when I apply an AND between these two numbers, 0xFF and hex 55, when I apply that AND, as you can see here, I have 55 in the output, like 1 and 1 is 1, 1 and 0 is 0, and so on and so forth. So here we did reset some bits in the FF number, hex FF, using the 0x55 bit mask. So we masked some bits of the FF using the 55 hex 55 bit mask, and this way we successfully reset or shut off or turned some ones into zeros using another value. Same here, I have 0, which is all zeros in a byte, and I have the same bit mask. When I apply an OR now to this initial value, which is 0, I get the same thing. And here I did set, I didn't reset. I set some bits of the initial value 00, 0 using the 55 hex bit mask. So I set this bit here, this bit, this bit, this bit, and this is called bit masking. So I used a binary mask to mask another value, and we'll see where this is gonna be useful for us in a minute. So here I have 128 in decimal, which is hex 80, or it's a single bit, a single set bit in an 8 bytes, in an 8-bit byte, an 8-bit byte. A byte is 8 bits, and I marked here the first bit purple. What I did here, hex 80, I did these two symbols. I'll talk about what do they do by one. So what I obtained is 64 in decimal, which is hex 40, and as you can see here, I shifted that bit one place to the right. So did these two arrows, one, I shifted this bit one place. Again, this number here, this hex 40, I brought it here, and I repeated this operation. I got 32 decimal, hex 20, and this bit is now shifted to the right twice. Now here became here, and this became this. I think you get what's going on here. Now, to drive this point home, this hex 20, I got it here. I shifted to the left now. I applied the opposite operation by 2. I got back to 128 decimal, hex 80, and I got back the bit where it's supposed to be. So as you can see, we shifted it right one place, then again one place, then we shifted it 2 places to the left. And this is called bit shifting. So now we're back here in the code, and this is I'll talk about these in a second. I guess now we're familiar with the word bitmask, so we'll talk about these in a second. We'll see this file which is here in a second. These are just constants. I wrote them in binary just to illustrate how everything is going. So let me go to the code and get back to these constants. We have two functions. We'll talk about these in a second. And here is our byte. This is the flag, the byte that I talked about in earlier. And here is the structure of that flag and what I'm keeping track of using one byte. So the first bit, I'm keeping track whether the user have won or not. So if this bit is set, the user has won. If it's not, the user lost. Again, since we can't use more than two helps at a time, and let me show you that it's still printing the pi. Let me reset. I'll ask if it's prime or pair or not. So it's pair. If it's prime or not, is not prime. And if I ask now if it's a multiple of 3 or not, as you can see, number is not multiple of 3. You've used all help available, which isn't permitted. So we lost. We want to try again. We done. So number was 14. And again, it gets back to printing pi forever. Anyway, so this is why we need to keep track of these three help states, whether the user have requested them or not. So we need three flags for these are used to keep track of these of whether the player have requested these helps or not. Then we gotta count the tries, and if you recall, we only have 3 tries. So again, we'll show you that I have 10, 12, and 15, and 16. I lost. So I have just 3 tries. No, so my number was 0. Anyway, so to count to 3, we only need 2 bits. So, and that's why I allocated 2 bits here for the counting of tries. Basically, I have 4 states, which is convenient because 0, 1, 2, 3. We can count to 4 states in 2 bits. So yeah, that's our flag. This is the number we're trying to guess, and this is just to keep track of time because of that printing are you there or not each 20 seconds. These variables here are used to parse the data from the user. That's why we don't need more than 5 characters, because no command surpasses 3 or 4 characters. And this is the printing buffer. It's just a buffer I'm using to print to the serial monitor. Anyway, so here we're at setup. As you can see, we're not doing much. So we're initializing our serial monitor. We're seeding the random number generator, and then we're printing the high message. And this high message is stored here. As you can see here, I have this program keyword, so I switched to an Arduino and I'll compile. We used 1055 bytes. Octet in French means bytes in English. So we used 51% of the dynamic memory, and the maximum is 2 kilobytes or 2048 bytes. Anyway, let me show you when I remove this, and an error happened. Memory insuffisant, which means not enough memory is available. And as you can see here, we used 2263 bytes, which is 110% of the dynamic memory. If you look here, we're only using 25% of the whole programmable flash, which is 32 kilobytes. So what is happening? In fact, this program keyword puts this whole string in flash, not in the RAM section, which frees up space for the RAM, because we need RAM to run our code. but this is static, like we're not changing this, so it doesn't make sense to put it on RAM. Same here with the 1024 digits of pi. The first bit mask that we're using is here, flag and state bit mask. And as we've talked about the bitwise and, here we're using this bit mask to set or reset. In this case, since we're using an AND, we're resetting some some bits of the flag. So let's check what are we doing. So we have here the state bit mask. As you can see, it has 6 zeros followed by 2 ones. So when we AND the state bit mask with the flag, we are ignoring all these bits and we're only keeping these 2 bits. So if we have here a 3, like if we have in the these 2 bits, if here we have like a 3 in the flag, ANDing the flag with this state bit mask will will delete all these and only keep us the value stored in these 2 bits. So yeah, so this way we can isolate these last 2 bits and count the state using them. So case we have a reset, and as you can see, I numbered the states here in like reset is 0, interact the second state is 1, 2 for the prompt, and 3 for the halt. We're using these 2 bits to the fullest, let's say. Anyway, so in the reset state, we're just resetting the flag. We're generating the number. It's random between 0 and 20 is the number. We're just printing like the game started message. Then I'm doing another bitwise operation. I'm doing here a flag and the not of the state bit mask or interact. So let's approach this part by part. Say our state bit mask is equal to 0b 00000011. This is our state bit mask. The not our state bit mask, this is our lambda, so it's 0b 11111100. And we end this with this value, which is the not of the state. What do we keep? So 0 and 1 is obviously 0, 1, 0, 0, 0, 1. So these are the first 6 bits, which, because we're ending something with a 1, we're passing the value as it is. So this is equal to this. Then we have 2 zeros, and here we have 1 0. So now in these we'll have 2 zeros because we're ending anything and 0 is a 0. So here what we did is clear the state mask. We cleared it. Why? Because we want to put in it another state, a new state, which is the interact state. That's why when we OR this, the interact state, this value, so we set the first bit, we get this value, and we just set the first bit. I hope this is clear. So we have our flag. We only clear the 2 state counters. Then we put a new value in them. And as you remember, since we're using an OR here, we're not changing this first 6 bits. We're only changing these 2 bits. Anyway, I hope this was clear. So this is how we jump to the interact state. And we start counting our time to print the you there message. So we go into the interact state. Here we're just checking if we've passed 20 seconds, and we print you there each 20 seconds, and we reset our counter. Easy stuff. Here I'm checking if the 3 bits of the help are set. So I can use this, but use this here just for clarity reasons. So as we discussed earlier, if we use OR, we're just combining the ones that exist in this bit mask, in this bit mask, and in this bit mask. So these three and the flag, as you can see, we have one here, we have one here, and one here. So these would result in this bit mask, which is the help bit mask. As you can see, one, and one. We want to see if these three combined ANDed with the flag would give us the help bit mask. This signifies that all help flags are set. If all three bits are set, we print you've used all the help available, which isn't permitted, and we go to the prompt. We're checking if read ser or serial. Let's see what that function does. It checks if serial is available. If not, this while loop, we want to enter this while loop if there's nothing in the serial part, and will just return false. Whereas if there's something, we'll read it, and as long as we haven't read the end of line character, which is the end of the command, I decided to make it the end of the command. You can make the command end with whatever character you want by changing this. And the index is less than 5. Why? Because as you remember, this is a table of character with length 5. So to not overflow this, we reset our index and we return a true, which means that we've read something. We didn't interpret what we read, we just read something. If we read something, if it's an H, if you recall, I'll print it here. So if it's an H, we print this message, this exact one. So if it's an H, serial.println hi, the hi message. If it's an N, and this ends here, so this is the case where we received an N. So we received an answer, an actual answer. We copy that, the value that we read from the first, remember we're counting from 0, so we ignore this N, which is in the 0th position in our buffer. We start from 1 and we read 2 characters, which is what we need to represent a number between 0 and 20. We copy these 2 characters into this S table of characters, and we do str to long. We convert that S string to a long, which is an integer. Anyway, I'm turning it into an unsigned. This is, by the way, an unsigned integer of 8, which is a byte. So on a base 10, because the number that we inserted is base 10, it's a decimal. So if we inserted a hexadecimal, we will have to use 16 here. Anyway, so here we have our answer. So if the answer is equal to the number, which is the right answer, we set the win bit mask, and notice here that I did or equal, which translates to I don't want to ruin the other content of the flag. I don't like just do this, because if I do this, the flag would only be equal to win bit mask, which is equal to 1 0 0 0 0 0 0 0. So I'll erase the state I'm in, I'll erase the number of tries I'm in, and I'll erase all the flags that I set, and I'll only keep this bit, which wouldn't help. That's why we add that or. That's why we do flag the other values, we preserve the other bits, and we set the win flag or the win bit. So that's what's happening here, and as discussed before, this is going to the prompt state because we got the right answer. So we gotta announce that they won and reset the game. Anyway, so this is in case we have the right answer. In case we have a false answer, what you will do is, here is the trickiest part of bit masking. So if you recall, the number of tries, we are keeping track of that in these two positions. And remember, this is still a byte, this is still an integer. So the value of flag, even if, like, say we do a flag and, just as we're doing here, if we do a flag and the tries bit mask, yes, we'll isolate these two bits. We will isolate these two bits, but these two bits aren't counting from 0 to 3. In fact, they are counting from, say we want to increment this. This is not a 1, this is a 4, as you can see. Say, increment this and further. This is an 8. Then we'll have our 12. Why? Because the positioning of these, the indexing of these bits matters. So we can't just end these like we did here with the state bit mask. We have to do something else, an additional operation. So here we are ending the flag with the tries bit mask. Then we're bit shifting these two bits, or the whole byte shifts to the right by two places. So what does that do? We have 4 zeros, then our 0 1, and then 0 0. And what we did by shifting them 2 places, we would have 0 0 0 0 0 0 and 0 1. And here you can see we're actually accurately counting from 0 to 3, and this is what we want. So this is what's happening here. I got the tries. I isolated the tries with using the tries bit mask. Then I shifted these tries by 2 bits to get the accurate count. Then, if the tries are 2, again, where we have 3 available tries, which is 0, 1, 2. 2 is our maximum, not 3, 2. We're counting from 0. What we want to do, if tries is 2, game is over, we go to the prompt state. Else, we still have tries to do. We have to increment that counter. But remember, we can't just increment it, because incrementing the flag by 1 would mean that, say the flag is all zeros, 1, 2, 3, 8, yeah. So, but say the flag is all zeros. If we add 1 to it, what would happen is 0, 0, 0, 0, 0, 0, 0, and 1. 1 will be placed here, and that wouldn't help in our tries, because if you recall, our tries are here in this location, in the 4th and the 8th 4 decimal and 8 decimal positions. So what do? So we increment the tries, then we bit shift them to the left by 2 to put them in the right position. Then we OR them with the tries bit mask. We do this like just as we're doing here with the state bit mask. We're clearing the counter, and then we are rewriting it with the OR operation in the right place by bit shifting this tries +1 to the left by 2. I hope this is clear. Like, try to write this down. If it isn't clear enough, like, try to write it on a piece of paper and do the bit shifting and see how it's working. Anyway, so yeah, this is the, in case we've entered the answer. Anyway, else, not else, it's a switch case, like, so not exactly else. Here we have, if we're requesting whether the number is pair or not, so we have, if you remember, like, the pair and prime both start with P, like here, both start with P, so buff of 0 is P in both cases, and we have to test the second character. So if the second character, which is buff of 1, is equal to r. We just test if the number is prime. If it's prime, we don't enter anything, like the number is prime. If it's not, we enter a not into this place. So, and the is prime function isn't like optimized or anything. It's just brute forces into it because we're just counting to 20, so it doesn't matter. If the number is less or equal to 1, 0 or 1 are both not prime, so we return is prime, we return not or false. Else we start by 2, and we're only checking to the square root of n because that's enough, and we're just checking if n is divisible by I, and if n is divisible by anything other than itself, then we return false. Else, if we reached here, so n is not divisible by anything but itself, because we can't reach n here, because so if n is divisible by anything but itself, we return false, else we return true. A very basic is prime function. There are so many ways to calculate the prime, to check if a number is prime, like up to 4 billion or something. It's way more efficiently, but here we're just counting to 20, so it doesn't matter, like it's in no time, like it calculates that in no time. So yeah, so we check if the number is prime or not, and we just print this this message, and here we set the prime bit mask again, just as we set the win bit mask. Same thing here. Else, so if the second character isn't an R, and in that case we are asking if the number is pair or not. So we just see if it's divisible by 2. If yes, it's pair. If not, it's not. So basic stuff, and we set the pair bit mask. If we're asking for 3, again, if it's divisible by 3. If yes, no, else not, and we set the 3-bit mask flag in the bit in the flag. If we entered an E, so we would print that the game terminated, and we would go to the halt state. Otherwise, if we entered anything else, we would have an unknown command. And in the end, we clear the buffer, we fill it with zeros. Very basic. Anyway, so this is our whole interaction. This is our whole game. Here we get to the prompt case or state, and here we're checking if the win bit mask is set. Again, by doing an AND, we only caring about the win bit mask with the bit that is whether set or not in the flag. That's according to the win bit mask. If it's set, we receive something. Again, a switch case. I love switch cases, and you have to use them all the time. Like, they are so useful. So we check whether the user have returned a lowercase y or an uppercase y. When I do this, like this case, this falls into this, and they both execute the same code. That's why this doesn't need a break, because I want it to go into this code if I have a lowercase y or an uppercase y. In that case, I just tell them your number was like wherever the number was, and I reset the I go to the reset state. If I received an n, a lowercase n or an uppercase n, the same way I tell them that here I tell them that I'm gonna restart the game. Here I'm gonna tell them that we're gonna terminate the game, and we're gonna halt. We go to the halt state. Else, If they wrote anything, I made it defaulting to now. So tell them the number again and go to the hold state. And if we timed out, which means like done is still is still false. We didn't read anything from the serial monitor. We timed out, so we defaulted to no, and same thing, we go to the hold state. And in the hold state, pretty basic. Each half a second, we would print the second digit of file, and that's it. End of hold state and of the state machine, the hold state machine. And this is our game. I hope you learned something. I hope you enjoyed this, and I hope my explanations were clear enough. And this is our game. Let's try to beat it once. See if it's a prime number or not. So the number is prime. Okay. So the number is prime. And let's see if it's pair or not. And the number is not pair. So what do we have? It's prime and is not pair. So it's not 2. We have, let's try 5. Let's try 5. So it's not 5. Let's try 13. It's not 13. Let's try, say, 17. And I lost. What was the number? The number was 7. And yeah, that's it. Thank you for your time, guys, and hopefully, as I said, you've learned something. And see you in the next video. Goodbye.